Hey everybody, we are going to move on to chapter 52 and population ecology. So this is going to be the study of the factors that affect population size and composition. And so when we talk about populations, we're going to be looking at individuals of a single species that occupy the same area. And we're going to be looking at what we call population dynamics. So we're going to be considering things like the number of individuals that are born into a population and the number of individuals that immigrate into a population. So that's the way you add individuals. And then also how we take individuals out of a population. And so that would be through deaths and emigration. A couple important characteristics that we need to talk about with populations are both density and dispersion. So when we talk about population density, we're talking about the number of individuals per unit area or volume. And so this is really important that we attach some type of area measure onto our population density. So to know that we've got 5,000 trees isn't super important, but if we know that we've got 5,000 trees for every kilometer squared, that's really important. Having 4 deer doesn't give us a lot of information. Do we have 4 deer in 1 kilometer squared, or do we have 4 deer in 50 kilometers squared? There's a big difference there. So make sure that anytime you're talking about population density, you include some type of area along with it. Next, we've got dispersion, and this is going to be the actual pattern of spacing among individuals. And there's 3 general types, clumped, uniform, and random. So here you can see the example of clumped, and so we've got a group of starfish together. Uniform is when the spacing between individuals is pretty constant, and then random is just that, the spacing between individuals is random. So clumped dispersion may result in forming a patchy environment, and it can actually increase chances for survival. Some examples other than the picture would be schooling behavior in fish or flocks of birds. Uniform dispersion is often the result of antagonistic interactions between individuals. And so a really good example would be with territories, or like if birds have a certain territories, you tend to see birds get as close together as they can without overlapping territories. You could also see this with the spacing between desert plants. And then random dispersion is usually the result of or absence of strong attractions or repulsions between individuals, and this is not a very common pattern. Next, we're going to talk about demography, and this is the study of the vital statistics that affect a population size. So this would be like looking at birth and death rates. So demographic factors that we need to consider are the age structure of the population, so how many individuals are there at each age level, birth and death rates, generation time, and then the sex ratio and reproductive behavior. So we oftentimes use life tables as a way to sort of summarize the mortality information for a cohort of individuals, and this is actually something that was developed from life insurance studies. But something that has a very real application in ecology. So what we're looking at here is a table that shows on the far left we've got the age, so the number of years. Then we look at the proportion of females weaning a litter. Then we look at the mean size of litters, and this is all males and females together. And then we're going to look at the mean number of females in a litter, and then the average number of female offspring. And so this is a reproductive table for Belding's ground squirrels, and it's giving us some information here on the number of females that have just reproduced, so that's going to be the females at each age that are weaning their litter, the overall litter size, the mean number of females, and then the average number of female offspring. So life tables will also show mortality rate per year. It can show the lifespan of the organism and the fecundity, or the essentially like the reproductive success, the birth rates. We can also look at what's called survivorship curves, and these plot the numbers of individuals of a cohort that are still alive over time. And we tend to see 3 general types of curves. So we call them type 1, type 2, and type 3. And you can see them here, the 3 different types of curves. Now the type 1 curve, if you notice, we've got the this is the maximum lifespan, and we've got the number of survivors, and this is on a log scale. So the number of survivors really early is really high, and so you can see for type 1 curve, we are an example, and then survivorship tends to decrease fairly quickly as individuals get old, With the type 2 curve, it's pretty constant. And then with the type 3 curve, you have much lower survival early on, but then the individuals that do survive after a certain point will do fairly well. So again, type 1 is low early deaths and then high late deaths. Examples would be us or other large mammals that receive a lot of parental care early on. So you have a higher survivorship of children and infants. Type 2 curve is a constant death rate. This you tend to see in annual plants and invertebrates. And then the type 3 curve, you have a really high number of early deaths and a much lower number of late deaths. Trees are a really good example of this. So curve type can actually change between young and adults. So a good example would be with birds. So nestlings tend to show a type 3 curve where more of them are dying early on, and then once the birds reach adult, then it's a pretty steady rate of death, and so it switches over to a type 2 curve. So life history strategies are really important when we talk about populations. They are the product of natural selection, and there's different types of life history strategies. You can favor maximize survival, or you can try to favor maximizing reproduction. So, two different examples of life history strategies. The first is simulparity. This is a one-shot reproduction with many offspring. So, salmon are an example of this. So, they reproduce once. So, they've got one shot at this, but they produce many offspring in that one shot. And then iteroparity is when you have repeated reproduction events, but you tend to reproduce with fewer offspring each time. You also can talk about opportunistic species versus equilibrial species. So we tend to call them R species or K species. So R species increase fitness by producing as many offspring as possible. So they do this by maturing early, having many reproductive events, and having many offspring. The result is that you maximize reproduction so that at least a few offspring survive to the next generation, but most offspring will die, so it tends to look like a type 3 curve. Then you've got K species, and these try to increase fitness by having them most of their offspring survive. So they do this with high parental care, maturing later, having fewer reproductive events and fewer offspring, but providing more care to the offspring that they then have. So the result is that you are maximizing survivorship of each individual offspring. So you have fewer offspring, but most of them will survive, and so this corresponds to a type 1 curve. So here's your lecture question for today. So I want you guys to think about, for a weed or for maybe a large endangered species or for a garden pest, what strategy do you think each of these types of organisms would use? Are these a K species? Are these an R species? So please send me an email to my to the class website and let me know what you think. Thanks, guys.